Okay, so now we are looking at the topic which is called analysis of variance, which is called ANOVA. Okay, it's a cardinal topic in quantitative method, in DMT, which is on decision making techniques. All right, so we'll get down to the details of this course so that you understand thoroughly. Okay, so under this topic, which is analysis of variance, we have a one-way ANOVA. So one-way ANOVA and two-way. So we have both one-way ANOVA and two-way ANOVA. Okay. So this is about what we are going to look at. So I'll explain the details of the analysis of variance, be it a one-way ANOVA or two-way ANOVA. So we'll look at both of the ANOVA. Okay, so now, before getting to an example, quickly, I need to explain the distinction between one-way ANOVA and the two-way ANOVA. All right. So one-way ANOVA is called a completely randomized. So under one-way ANOVA, we are simply saying this is a completely, it's called a completely randomized design experiment. So completely randomized, okay, randomized design experiment. So please take note of this term. So I'll be a little bit slow to explain because I need people to understand, and you need to know that this is the cardinal topic in quantitative method. All right. So under this one-way ANOVA, there are three measures we consider. So three parameters. So we have three parameters. And then I will explain the reason why we look at ANOVA. We analyze the variance in a field. You find this field is giving you the good yield. The other field, it's not giving you the good yield. So we are now analyzing the variation, analysis of variance. So sum of square of total, that is the number one parameter. So we have sum of square of total, all right? That is one parameter here. The second parameter is sum of square of treatment. So sum of square treatment. And then the other one is sum of square error. Okay. So this is the second component in one-way ANOVA. Number three is sum of square of error. Sum of square error. So this is about what we know, what we need to know. Okay. So the ANOVA table for one way is given by, okay, so ANOVA. So we have ANOVA table. So ANOVA table for one way. Okay. So ANOVA table for one way. We are going to have the table should have okay. So your first one is source of variation. So in this table here, we have the following. Okay. So we have, so the first one is source of variation. So we have the source of variation. So the source of variation, source of variation. So source of variation here, source of variation. Then you have sum of square. So SS is sum of square. Then you have the degree of freedom, which is DF. Then we have the mean square. And then we have the F calculated. So this is about the table to go for. So there are only these parameters we need. Okay, so there are 1, 2, 3, 4, 5. Okay, so here we have sum of square of treatment. Okay, so treatment. Then you have sum of square of error, sum of square error here. Then we have the sum of square of total, sum of square total. So this is about what we need to know as we look at the ANOVA. Okay, so this is on one way ANOVA. Okay, so now getting down this table, we're supposed to present it. There are no blocks for one way ANOVA. So the sum of square of total, the formula, they may not be given. These formulas are not given. So we just need to understand them. So sum of square of total is equal to, okay, summation of x, okay, square minus summation of x in brackets is square. All right. Then we divide by n, capital N. So that is sum of square of total. Okay. Then sum of square of treatment is actually given by, so treatment, sum of square treatment is going to give given by summation of t I square, okay, over small n, then minus summation of x square over capital N. Okay, so this is about the formulas that we need. They may be provided in the exam, or it's up to the examiner. So now sum of square of error, okay, is equal to sum of square of total. So sum of square of total, okay, minus the sum of square of treatment, minus sum of square of treatment. So this is about why we are looking at the analysis of variance. So this is one way. So the degree of freedom will be given here. Okay, so sum of square are the figures that we get here. Sum of square total, sum of square error we put here. Okay, so these ones are put here, the sum of squares. For the treatment will come through, which is this one is sum of square treatment, which will be there. As we find using that formula. That one of the total is the one that would come here. And that one of the error is the one that should come on this one. Should come here for the error. Okay. So this is about the degree of freedom is k minus 1 where K is the number of treatments, so K minus 1. Then getting down to the error is N minus K. And then getting down to the other one, it's N minus 1. So this is about how you get this one. Okay. So this is mean square, we divide the sum of square divide by the degree of freedom. So it's a sum of square divided by the degree of freedom, which is K minus 1, where K will be there. So about that, we are getting that one. So each of these ones, they are handled accordingly. So even here, we can have the sum of square of error. Okay, we have this one. So it is the sum of square, then you divide by N minus K. For this one, we are simply saying the determinant here in this case is the sum of square of error is a determinant. All right, whether it's for one-way ANOVA or two-way ANOVA, the determinant is the sum of square error. Sum of square error is a determinant as we are looking at these ones. All right. So this is on this topic. The F calculated, we are going to say it's a mean square treatment, mean square treatment. Okay, then you divide by the mean square error, the mean square error, which is the MSE. So we are going to understand thoroughly this table as we look at examples. All right. So this is about the one-way ANOVA. There are only 3 parameters. So this is analysis of variance for one-way ANOVA, which is called a completely randomized designed experiment. Completely randomized designed experiment. So let's now go into the other one, two-way ANOVA. So let me quickly now look at examples with a reference to the formulas that are here. Then that will mark the end of the topic, okay, in terms of both the one-way and the two-way ANOVA. So two-way ANOVA, okay. So under the two-way ANOVA, we have 4 components, okay. So this is called block design experiment. So it's a block design. Okay, so it's a block design experiment. Okay, it has both the treatments and blocks. Okay, so we have this one. All right, so now we're getting down to 4 components or 4 parameters that are here. So we have 4 parameters or 4 components. So this one, we are looking at why are we having a variation in the field. So we're looking at why you are growing tomatoes in one field, the average yield is different from the other field. So you're wondering as a farmer why you are having those variations. So the first one is sum of square of total. Okay, so 4 considerations of 4 components total, which is equal to summation of x square minus summation of x in bracket square over n. Sum of square of treatment, okay, which is equal to summation of ti square over n. So this is just a square here. Then minus summation of x, okay, summation of x square over n. Sum of square of blocks, sum of square of blocks is equal to summation of b square over n minus summation of x square. Okay, so x square over n. Okay, so we have now the sum of square of error. Sum of square of error is equal to sum of square of total. So just the presentation, sum of square of total. All right. Then minus sum of square treatment. So treatment here. Then minus sum of square blocks. So this is how you get the sum of square of error. Now getting down to the analysis of variance table for one way Anova. That is for two way Anova, at least one. So Anova table for, okay. So we have Anova table for, so you have Anova table for two way. So Anova table, okay, for two way. Okay, so for two way, we are going to have the first one. Okay, so we have this table here. Okay, so under this table, we have the first one, which is the sum of square. Okay, there should be 4. So here we have the source of variation. Then we have the sum of square. Okay, then we have the other one is the degree of freedom, which is the df, degree of freedom. Then we have the mean square. And then we have the f calculated. Okay, so this is about, so the first one, you're getting down to sum of square treatment. Then we have sum of square of blocks. Then you have sum of square error. And then the last one is sum of square of total. All right, so this is about what we need to get as we are looking at these ones. So here you can put the figures here based on the formulas that are there. All right, so even here we can put the figure here based on what we have. The degree of freedom is k minus 1. Then this one is b minus k. Then this other one, okay, is just the product of k minus 1 and then b minus 1. Okay, b minus. So this is b minus 1. Okay, so this one is a 1, not a k. So b minus 1. So it's a product of these two. B minus 1, k minus 1 is where k is the number of treatments, and then b is the number of blocks. All right, so this other one is n minus 1. So mean square is a division of SS then we divide by k minus 1. Then the other one is SS sum of square for blocks, divide by b minus 1. Then the other one is also about the same. So it's SS, okay? Then divide by the degree of freedom, which we have gotten there. So the determinant is the sum of square of error in order to find the F calculated. So to get F calculated, it is the mean square treatment of a mean square error. So mean square treatment divided by the mean square error. So mean square error. So this is how we get the F calculated for each of these ones. Then the other one, getting down to the F calculated for blocks, is mean square blocks. We divide this one by the mean square error, MSE, which is the mean square error. All right. So here we don't find for this one and this one, we don't find the F calculated for these ones here. All right. So this is another table for 2A. All right. So we have this given. These are the two tables, and the formulas I've given for 1 way, for 2 way. So here we have 1, okay, that is the 2 on the sum of square treatment, sum of square of blocks. Then we have also sum of square error. The tables, all the tables are given. Please, if there's any question so far on the tables, feel free to ask a question before we get quickly in 30 minutes time about into calculations of questions that came in the test paper. We'll get examples from the question paper. All right, so these are the formulas to use as we are looking at a one-way Anova and then a two-way.
Mr. Stan,
Yes, please.
only go back on the other.
Okay.
Yeah, this one. Only sum of square treatment. Say it is equal to summation of what?
Of t square. It's a square. This one is a square. Summation of t,
T square.
T square.
What?
So this is the square here. It looks like a 3, but it's a 2. It's a square.
Okay.
So summation
Then
of also over
minus open bracket is summation of what again? Of 2.
summation of x square. This is summation of x.
X.
This is summation of x in brackets is square. Then divide by capital N. Here we're dividing by small n. I will show you the distinction between the small n and the capital N as we look at the actual question.
Okay, and what is T? It's given.
Which one?
T.
The T is the treatment. So T is representing the treatment. So meaning the treatment 1, maybe it is the product 1. You know what I mean? Product 1. Okay, so that is what happens. So at the time we'll be adding them. So you understand this one thoroughly. So even for this one, sum of square of blocks, summation of b square, which means blocks square over n. So I'll break down this formula so that you understand what the t represent.
Okay.
So I'll explain thoroughly where you understand what the t represent and what the b represent. So for this one, then on the first part of the formula here, where we are finding summation of x square minus summation of x square over capital N. Here, you just need to enter the data set in the calculator. I will show you how to enter the data set in the calculator quickly so that you understand how we get a total. Then the sum of square of error, sum of square of total minus sum of square of treatment minus sum of square of blocks. This is for a two-way Anova. All right, so I'll get into details of how we getting down to the treatments and the blocks. All right, so let's look at the actual question so that you will now see what is actually happening. All right, so we can go to this one. Okay, so question 4, a study was conducted in a certain town in Zambia. The aim of the study was to compare the mean. In fact, first and foremost, I would have to make mention that before we go to the question, I have to make mention that in ANOVA, we always test for the mean. We always test for the mean. So we always test, okay, for the mean. So this is what this ANOVA is all about. Okay. So now, e.g., H naught mu1 is equal to mu2. So we're simply saying in every field, the mean, the average yield is the same. Okay. So average yield is the same in field 1, in field 2, in field 3, in field 4, in field 5, and all that. Then this H alternative, which is H1 or HA, we are simply saying at least one of them is different. So at least one of them is different. Okay. So this is it on the aspect of testing. So we always test for the mean as we are looking at analysis of variance. All right, so now we getting down to this example quickly. So here we are simply saying, so by virtue, so this is an ANOVA table, they're saying complete ANOVA table, but now before that, they're saying a study was conducted. So quickly now we can get to this example. A study was conducted in a certain town in Zambia. The aim of the study was to compare the mean supermarket prices of 4 leading brands of detergents. That's the Boom, Bullet, Dynam, and Waco. 10 supermarkets were selected, okay? And the price per gram was recorded for each brand in each of the supermarket. The experiment was done as a randomized block design. So it's a two-way ANOVA straight away, like I mentioned. So when you are looking at the block design experiment, we are simply saying it's a two-way ANOVA. Write the appropriate model and give meaning of all items in the model. What are the blocks? What are the treatments and experimental units? Complete the ANOVA table. All right, then getting down to part D, using the information, test for the no difference among the treatments at 5% level of significance. What's your conclusion? Then if the data was analyzed as completely randomized, which is one way ANOVA, what would have been the conclusion? All right, so now let us get down quickly to the solution here on question number 4. So here we have the treatments. The sum is that. The blocks we have, so meaning this is a two-way ANOVA. We have the source of variation, sum of square, degree of freedom, mean square, and def calculated. So these are the 5 standard columns. So variation, sum of square, like the ones I gave, the degree of freedom, the mean square, and def calculated. All right, so now we are now getting down to question 4. So the model, so the solution here, we are simply saying the model, we have y is equal to mu plus treatment plus blocks plus error. So this is what is happening here. This model, it is testing for the mu like a two-way ANOVA. Okay, so two-way ANOVA. So we are simply saying we have been given, all right, the compositions of we're testing for the mean. All right, now getting down to the treatment, which is a TI, the blocks, which is the B, then the error, which is the E. So this is a composition of these in the model. The I represent the treatment, then the B represent the J here represents the blocks. So this is about what we are talking about concerning this question. So we have testing for the mu, then testing for the treatment blocks and error, because the error is there. Then the I is representing treatments, the J the blocks. Okay, so we have this composition over mean, effect, detergent, effect on treatment, the blocks, the residue, which is the error. So these are explained here. All right. So the aspect of question 4 is here with us. All right. So we have the mu, testing for the mu, like I mentioned for ANOVA, we test for the mean. The treatment should be there tested for. The blocks error should be there. Then that we have I is representing treatments, the T, and the blocks we have that. So this one,
The first one is YJJ.
Yes, this is YIJ. YIJ, meaning this is meaning that this YIJ, the I is representing treatments. Okay. So this is a T. Then this J is representing the blocks. Okay. So this is what this one is about. So we have the I representing that one, and then the J is representing the blocks. So the compositions of these items, testing for ANOVA, we test for the mean, the treatments, okay, to make a conclusion, the blocks and error. So this is why we have this kind of equation or model, so to speak. So
these letters, are they standard, or we have to put a key to tell the examiner what the I and the J represent?
yes, you just it's a guide, it's standardized equation that you need to, but you can also put somewhere what the I represent. Like here, the I can be 1, 2, 3, 4, up to whatever number of treatments that are there. Getting down to the blocks, we can find if there can be 1, 2, 3, 4, up to a number of blocks that can be there. But you need to just indicate that the I represents the treatments and then the J represents the blocks. So the breakdown of these, there's no problem. You can go through here, the mean, the effect due to the detergents, the effect of the supermarkets. So those are the blocks. Because you see, why are we saying supermarkets are the blocks? Because it is in the supermarket that those detergents, the Boom, the Waco, that's where they were sold. So this is it, the way we have this one. Okay. So we have these compositions, the residue value and other components. Okay. So we are now getting down to the second part of the problem, where we're saying the treatments are the detergents here, because the question was saying determine which ones are the question. Okay, so the question was saying which one is okay. So what are the treatments, blocks? And so the first question has been answered. B quickly, we'll go to B quickly. We have which ones are the blocks, which are as a treatments and all that. So getting down here, treatments are the detergents. These are the treatments. And then the blocking are the supermarkets. Okay, so that is where the detergents can be sold in those supermarkets. So the experimental units are the prices of the detergents at 10 supermarkets. That is, experimental units are the prices of the detergents at the 10 supermarkets. So this answers part B of the question. All right, now let's get us getting down to the other one, which is the part C, complete the ANOVA table. So on the completion of the ANOVA table, it's not a cumbersome way to go about it, because the total should be 22.94. So you can find what is for the blocks. So for the blocks is just the subtraction, because when you add all these three parameters, the treatments, the blocks, the errors, we should get a total of 22.94. So I was completing the ANOVA table. This is what happened here. So the degree of freedom, we will get down in it because for the treatments, we have 4 detergents, that is Boom, the Bullet, the Dynamo, and the Waco. So we have these 4 treatments, but the blocking aspect here was the 10 supermarkets. All right, so the 10 supermarkets were selected. So these were the blocking aspect of it. All right, so this is just paying particular details, particular items to details according to what we're having right about now. Okay, so we are getting down to this one. So sum of squares is 5. The 5 is coming from the way it has been given here. Then getting down to blocks, 17.45, that's the subtraction from what was missing here to get a total, meaning that it's just about 22.94, then minus the 0.49 minus 5, we are getting 17.45. That is where that one came from, 17.45. The degree of freedom, the treatments, they were actually 4, which is the K minus 1, based on the table which I gave out. So this is 4 minus 1. The blocks were 10 minus 1, because here the degree of freedom is K minus 1. All right. So quickly, we can look at this other one. So this is also B minus 1. So it's just about that. And then we are getting down to these figures. Then when we divide to find the mean, we are dividing the 5 divided by 3 to get the mean square. All right. So to get the mean square, we are just dividing the sum of square divided by the degree of freedom, as per the other document that I shared concerning the one-way and the two-way, where we are looking at the division here on these ones on a completely randomized design, or on the block design experiment, where I gave the how we are getting the mean squares. All right, so this is about what we are looking at. Okay, so we can continue here where we are getting this division. Now this one is a constant. The sum of square of error is a constant value. So when we divide this one by the mean square, we are getting the 92. So this, we are dividing this one, we are dividing by the mean square error to get the F calculated for that one. Then even 1.9389 divided by 0.0181, you're getting 107.125. So we are dividing this by this mean square error. This one divided by the mean square error, we are getting this amount. Then this one divided by the mean square error, we are getting that amount. All right. So this is about how we are doing this. Now, conclusion. They are asking us that. Okay. So here we are being asked, use the above ANOVA table test, okay, to make a conclusion at 5% level of significance. So we can conclude using that. All right. So meaning our conclusion, we are here to say, okay, on the treatments, there were 4. So meaning treatment 1 should be equal to treatment 2, should be equal to treatment 3, should be equal to treatment 4, meaning that the average number of detergents, okay, so detergent 1 for Boom, for Bullet, for Waco, okay, and the other one, they are the same. The mean difference is the same. Okay, so we can go for any one of these detergents, but alternative simply means at least one of them is different. So this is a hypothesis test for this given ANOVA. Okay, now reject H naught if F calculated is greater F, the degree of freedom for treatment, and degree of freedom for error. So degree of freedom for treatment, which is a 3, and degree of freedom for error, which is 27. So from the statistical tables, from the tables of statistics, we came here to find the 0.05. Okay, so 0.05 here. The F calculated for treatment is 92.0829, which is this one in the table. All right. So 92.0829. If it is greater 2.9603, this one is obtained from the table. Degree of freedom for this one is 3. Okay, so it's a 3. And the other one, degree of freedom for error is 27. So based on this one, the 92.08 is greater than 2.96. So therefore we reject H0. So this is the rejection rule as we are looking at this one. All right. So this is the rejection rule. So we have rejected H0. Okay. So on the tables, we'll be able to show you thoroughly on how we get these figures in the table. So use the F table 0.053. There are 3 as a numerator and 27. You can get the 2.9603. For those who will be behind getting from the table, we'll be able to explain thoroughly how this figure was found. But you go to the F table, statistical table, you will go for F table 0.05 and you go for 3 and 27 to give you 2.9603. All right. So now getting down to, if the data was one way Anova, it's the same presentation, except that it's a 5 there. So error, the total still remains the same. So the error will be the difference between those, meaning that the blocks should not be there for a one-way Anova. They are not supposed to be blocks. So you're getting 17.94, which is error. And then to get the mean square, you're simply dividing 5 divided by 3. You are getting that column there. This one divided by 36, we are getting the other column, this other side. Then to get F calculated, it is the division of these two. This one divided by the error as a constant to get the figure here on that one. So we're supposed to, here we are saying hypothesis test, H0 mu1 for whichever detergent paste is equal to mu2, is equal to mu3, is equal to mu4. All right. So from here now, we are disagreeing on the alternative hypothesis that at least one of them is different. So our conclusion is that reject H0 if F calculated is greater 0.05, then 3 and 36. So there's also supposed to be a 3 here. So incorporate a 3 and 36, which is giving us 3.34 is greater than 2.866. So therefore we reject H0. So this marks the end of question 4, please. So you just need to go through these tables. These tables are given. All right. So this is about it. What goes on as we look at this.
Up a bit.
Yes, which one?
Hypothesis test. There where you wrote hypothesis. No, down, so down.
Here.
Yeah, that one says, is it HQ or it's H what?
Yeah,
under the
H0. H0, this HO.
Now the one below H0 there where you are.
It is HA, H alternative.
H alternative, okay.
It is also written like H1. If you don't want to go for HA, you can go for H1. The examiner was to accept. So meaning you're saying for now hypothesis, we're simply saying that all the mean yield or the mean for the detergents are the same. Against the alternative that they are not, at least one of them is what? Different. That's what this one represent. All right. So even for the other one, that's what we did. Okay, at least HA, HO. Okay. So this is now hypothesis. The other one is alternative hypothesis. So you again get these figures, the critical value of F from the table, where we are able to get them from there. All right. So this is marks the end of question number.
And so I was wondering, how do you know that this is two-way Anova and this is one-way on Anova? What do you look for?
Okay, like I mentioned, it will say for one-way Anova, as both treatments and blocks. So like this is a two-way ANOVA by virtue of looking at this table, because it has these two, the blocks and treatments. All right. So when you have those two together, then it's a two-way ANOVA. Like I even mentioned the other time that here, looking at this one, for a two-way ANOVA, when you have the treatments, we have the blocks, the error, and the total, because the two-way ANOVA is actually 4 components. Okay, so it has the 4 components here: the total, the treatments, the blocks, and the error. So if all these 4 are there, then it's a two-way ANOVA here. All right. Then a one-way ANOVA has only 3 parameters, which is the total, treatments, and error. Just these 3. So this is how you distinguish the other one from the other one. Have I answered your question?
Yes, sir.
Okay. So this is what goes on here. So we have this one. So we have answered question 4. Just need to go through these solutions that should be sent to you, these solutions, so that you can go through thoroughly on question 4. Now, let me just quickly look at question 5. So question 5, if you don't have blocks, the treatments are represented by columns. So if you go to question 5 is just a one-way ANOVA because it has only brand A, brand B, and brand C. So this is treatment 1 for the first one. So this is T1, treatment 1. This is treatment 2, and then this is it, treatment number 3. Okay, so these are the treatments 1, 2, and 3, and each of these treatments has 5 components in it. All right, so treatment brand A has the 1, 2, 3, 4, 5. Brand B has similar 1, 2, 3, 4, 5. C similar as all these 5 components. All right. So the following data are formed from a, so when you come across the term completely randomized design, simply means it's a one-way ANOVA, because I gave the terminology of a one-way ANOVA, which is a completely randomized design experiment. Okay. So I simply saying the following data from a completely randomized design of the lifetime order controlled conditions in hours in excess of 1,000 hours or samples of 60 watts of electric bulbs or 3 different brands. So the question says, drive a one-way ANOVA. Because it's one way because here we don't have blocks. The blocks are supposed to be here to represent the blocking parameter. No, but here we don't have the blocking factor. So this was just a one-way ANOVA. So we treat it as one-way ANOVA, which is a completely randomized designed experiment. So now we are supposed to develop that 10 marks. After that, these other ones are now, we always test for the mean difference. Okay, so at ANOVA, so at alpha 0.05, can we reject the null hypothesis that the means are equal? Okay, so can we reject the null hypothesis, the H naught? Okay, similar to the one we're from doing about right now. So here we are going to get down to the solution quickly so that I explain. Again, we get into the Fisher. Okay, the Fisher procedure for the confidence level. The Fisher simply means the least significance difference. Okay, so the Fisher simply means least significance difference. That's the meaning of the short abbreviation of LCD. That is the least significance difference. Least significance what? Difference. That's what it means. Even here, least significance difference. So quickly, here we can get into solutions as one way ANOVA. So meaning we are going to go for a table where we have only 3 parameters. One way ANOVA, the sum of treatments is given by this one. All right. So sum of t square over n and the summation of x square over n. Now this 150. So treatment 1 square, meaning that the total for brand 1 was 150. All right. Then but you square it. So if you come here, you find the total here is 150. When you get your calculator, get that one on 150. Then the other one is 225. So this is 225. Then the other one is okay. The other one is 180. So this is 1.8. So meaning this is how we first find the totals in each of these. So brand 1, brand 2, brand 3. All right. Then as we come here, we square 150 square plus 225 square plus 180 square for each of these brands, divide by n. Our n was 5. Why 5? We can count 1, 2, 3, 4, 5. That's where the 5 is coming from. So 150 square divide by 5. If need be, you can go 1 by 1, or 225 square divide by 5, or 180 square divide by 5. This is how we are getting to each of these values. All right. So now here, sum of square of treatment, we found 570. So meaning this one minus the summation of x simply means we add all the figures in that given parameter. So we add all the figures to find the sum of square, the sum of these. So the summation of all these here is giving us the addition of all these values here, meaning that you simply add 150 plus 225 plus 180. This is now about, we are getting 555, then you square over, the total is 15. This is a capital N. Our capital N is 15. All the numbers there, they were 15. That's what it means as we are looking at that. So the sum of square of treatment is 570. Then sum of square of total, using the same formula here, we found using this formula here, sum of square of total. Of course, this n is our capital N, which is 15. Then we can actually sort out. So the summation of x square. So you square each of the numbers. Okay, for those who be behind that much, you just enter the data in the calculator, each of these data in the calculator, and then you are going to find the summation of x square. So if you want manually, you can get n, you can say 32 square plus 30 square plus each of these numbers square. It will give us the value that we obtained, which is 21,171. So it is 21,171. So this is the summation of all those figures, and then summation of just x, okay, is 555. It is 555. This is the summation of x. Okay, summation of x square, we have the other one. So this is about how we get to these figures here. Then after that, there is need now to actually start finding. So the total is giving us 636, this sum of square of total. So we can find the sum of square of error simply by saying sum of square of total and sum of square of treatment. We are getting that. Of course, how many treatments are we talking about? There were 3 treatments. So K is equal to 3. All right. So since K is equal to 3, then we can set up the one way Anova table for this one. Okay. So meaning one way Anova table for this one, we are getting source of variation. It is sum of square of treatment. The sum is 570. The error is 66. Degree of freedom is K minus 1. Okay. Which is 3 minus 1, which is giving us a 2. That's where the 2 came from. Then this other one is the n minus k, which means our n is 15. The total 15 minus 3, which is giving us 12. Okay. Then we can start finding the mean. 570 divided by 2, we are getting the 285. All right, so this is just about how we are getting this. And then our F calculator is 51.818. Okay, so we don't have to find anything for this, for these ones. Just leave them empty. So we have practiced the Anova table. Now for B, we are trying to see H naught, the mu of 1 is equal to mu of 2 because there are 3 treatments. Okay, this is how you're finding this. And now hypothesis. H alternative, we are simply saying at least one of them is different. All right, so we reject H naught if F calculated is actually greater than alpha, which is 0.05. Okay, then degree of freedom for treatment, which is 2 and 12. So you're getting 51.818 is greater than 89. So therefore we reject H naught. Or alternatively, if the p-value is less than alpha, we reject H naught. But this is a cardinal one that you can go for, or now you make a decision. Okay. So yeah, now looking at LCD, which is the least significance difference. Okay, so this is least significance difference. So this is the least significance difference is given by the formula, which is
So on the B part, if the symbol there was 51.1 H18 less than the other one, it would have been what reject also.
would have accepted H naught. If this
So
figure
you
was
write the answer as accepted.
if this figure was actually less than this one, would have actually rejected H naught. All right, so would have rejected H naught. Now it would have accepted H naught if this figure was actually less than this one, would have accepted H naught. Now the way it is, we are rejecting H naught because we have the figure that we have calculated, the 51.818 is actually greater than 3.89. So we are rejecting H naught. If this figure was less than the other one, would have accepted H naught. All right, so now let's look at the last one, where we're looking at the LCD, which is the least significance. This is the least significance, difference. So least significance. So this L is for least significance, D stands for difference. So it is equal to T alpha over 2, then N minus 2. Okay, so N minus 2, there is a comma here. Then this one, it is 2 multiplied by MSE over N here. So here is capital N, or you can put just the, for since that one, so we're putting our N, which is like a small n here for the difference. Okay, so they're saying use the Fisher process to test the significant difference between the means of the brands. So means of the brands, each of those brands has N of 5. That's where the 5 is coming from. This MSE is a mean square error, which you can get from the table. The mean square error is 5.5. So this one is MSE. That's the meaning of that one. So it is a mean square error. So you can now sort out, substitute there, and then find the LCD. So our LCD here is the MSE. So 5 is coming from where this one we can obtain from the T-table distribution, which is giving us this. So from the tables, unless those who are behind, in the next class, I'll be able to explain thoroughly on how to use the tables. Then 2 is constant on the MSE, which is coming from the table over that. So our LCD is 3.23. So we are using the Fisher least square significance difference to test it, okay, to test whether there is a significant difference between the means. So reject H naught if F calculated is greater than FC. Okay, so that is on the least significance difference. Of course, 51.81 is still greater than this amount you found for LCD. So this is now you get the LCD, the least significance. S stands for significance, and then the D is only the difference. Okay, so D is for difference. So we are still rejecting H naught. Then the last one, confidence interval for the difference using the LCD. So X bar 1 is 30. So the mean of 1. Okay, so the mean of 1. Okay, so the average of each of these ones. Okay, so these means the average is it is 1. Okay, so from here the mean of this one was 150. The mean is, yes, the mean is 30. The mean here we can find the mean. So I want us to find the confidence interval for the difference, for the mean difference here. Okay, for the difference between the brands of those ones, the mean difference of those ones, we find for the mean. So we are getting the value which is giving us the X bar A minus X bar B. We are getting this. So here we are simply saying the difference here 30 minus 45 for the difference, the X bars, plus the LCD. So this one is LCD So we are actually now getting the confidence level, which is this is the final answer here that we have. So for the groups of brand A, we have 5 counts. For each of them has N 5 counts. The sums were 150. Then the average was actually 30 for brand A, 45 for brand B, 36 for brand C. So this marks the end of question number 5 on the one-way ANOVA analysis of variance. Please take time to go through the solutions. If they are not making sense to you, then we can again come through and run through, especially where people are behind. Is that okay?
Yes. Are you going to share the video immediately after the class?
So the video will be shared, don't worry about it. So you would need to go through the solutions. The formulas are given where you have a problem. We are going to come through, we run through again for those who are behind. So we'll find time to come and run you through. So the video will be shared. So we can end here for class. So you can start exiting because I'm supposed to use the same link for the other class. So please, you can exit
Are we going to use the same link in the at 18 hours?